the floor is yours.
Thanks a lot. So thank you for the introduction. And today I'm going to be presenting some work on dynamical low-rank Kalman filtering that I've been doing in the recent months with my advisor, Fabio Nobile. So let's just maybe jump right into it. We're going to be looking at a setting that is quite typical in the world of data assimilation. So you have essentially a dynamics, which is the signal here, or rather a signal which is, a signal which is driven by some dynamics that you have, in this case this linear affine model, and then you have some noise that you add. And you're observing the signal through some linear observation H, and those observations are noisy too. So you're in the typical setting of trying to recover as much information as you can from those observations to infer what the signal might be. We typically assume that the initial condition of the signal is Gaussian. That's more of a practicality. And so what I've said just before in language, you can say a bit more precisely in math. The idea of the filtering problem, as we're going to look at it for the next half an hour, is to essentially characterize this filtering distribution that you see here. So this eta, which is the law of the signal, given the history of the observations from time 0 all the way up to t. Here it's denoted by this sigma algebra of the observation process. Two more things that I should say on the slide. The first is that we typically work in a setting of data assimilation where you want to combine the ideas of the model that you have of the dynamics that evolve and the data stream. So we're going to assume that this sigma here is not too big, because essentially if you assume that your model has a big noise, then what you're really saying is that you are not sure how your model is evolving in time and what your signal is doing. It might as well be random. And at this moment, it might as well also be more interesting to look at more data-driven approaches relying solely on the observations. So we typically assume a small model noise in this work. And the second thing, which is quite typical in data assimilation applications, is that the signal lives in this space Rd here, which is typically going to be a lot bigger than the observation space K, Rk. And this makes sense. Your data assimilation might be the weather, so you have, I don't know, 10 million degrees of freedom of discretization, and you're observing the weather in a few weather stations, so you have 25, 30, 100 observation points, and you want to use those to recover some information about the full system. So that's the setup that we're working in.
Sorry, your F can be anything?
Which F? The first line. This line here? This is just some linear affine dynamics, so it could also be time dependent. It is an easy model. Yes, exactly. This is linear affine. So the reason it is actually linear affine in this talk is the fact that in this case we actually know the solution to the filtering problem, because it turns out that the filtering density, i.e. the guy that we want to compute, is at all times Gaussian. And this means that you can just characterize this Gaussian process by its mean and covariance, and you're done. You have completely characterized the process, and that is always good news. It actually goes even further, because we know what the evolution equations of this mean and this covariance matrix are in the case of this linear affine setting. So you have here the equation for the mean. As you can see, you're kind of mimicking the same linear affine dynamics from before. And then there is an extra term. I will get to this, and it will pop up naturally. And then for the covariance, it turns out that there is also a closed form equation which predicts how the covariance of your filtering system is going to evolve. As you can note here, it does not depend on the observation process, which is quite a funny feature in this linear affine setting. And this is called the Riccati equation. So that's a perfectly valid way of solving actually your filtering problem in the linear affine case. You just have to compute solve for the mean and the covariance, and you're done. This works. Doesn't work so well if you have a system where D is extremely large. Again, think of weather applications where you have millions of degrees of freedom, because then the covariance is going to be D squared, and that typically becomes intractable very quickly. You cannot even store this object, let alone evolve it over several time steps. It becomes a mess, and you need to find other ways to essentially track your filtering density. This is going to be the second approach. The idea that you could do is you could cheat a bit and consider some kind of auxiliary process, so another process which you can simulate, which has the same statistics or essentially the same law as the filtering density that you're interested in. So essentially you can try to hack your way and find a different process. Here we're going to be looking at the Kalman-Bussy process. And you can verify that if you look at this dynamics here, as you can see, it's very similar to the ones that we had before. You have the same linear affine dynamics here, and then you add this term here with some kind of mismatch between the observation stream that you have, taking the observation model that you apply to your process, measuring this mismatch, and then you left multiply it by something which depends here on the covariance. And so you can do some math and realize that this system here has exactly the same filtering density, has exactly the same conditional law as the filtering density. So solving for this is equivalent to solving for that one. But the signal you don't know, and this you're allowed to simulate. So this is a nice approach. I'm lying a little bit because this here is not yet a practical way of solving this, as this is a Makheen-Vlasov equation, and you kind of need to know the covariance of this system to solve it, which is quite tricky to do, and is in essence almost equivalent to solving the first problem. What you can do is you can go with a particle discretization. So essentially you consider an ensemble of p particles, and you let those represent your empirical measure. So you try to essentially replicate the filtering measure by this discrete sum. So what you do is you define here the sample mean, the sample covariance in the second line, and then you look at this so-called ensemble Kalman filter, and that is going to be one of the central pieces of this, of the exposition. Essentially, you have again the same story, so you're now letting each particle evolve according to its own dynamic, but you couple everything again through this mismatch term, and now here you have the sample covariance, and that is a computable quantity. So now you have a set of p particles which evolve in time, and essentially they kind of match or approximate the filtering density that you're after. This is a practical algorithm, and it's used very often, in fact, when you're dealing with high-dimensional systems, because as we said, it allows to evolve to explicitly compute this high-dimensional covariance matrix. So that is a good news. There is, to be fair, also some bad aspects of this system. So just to briefly go over them, it turns out that in its most basic form, it tends to be quite often unstable. You need to do like some extra work of stabilization to make it work and to have it not blow up in several ways. But let's assume that this point is handled. Then there is another point, and this is almost, trivial or obvious to say, but the cost of simulating this ensemble of p particles scales like the product of both the number of particles and the dimension of the state, right? If you have essentially p particles and each particle has dimension d, you need to store d times p and evolve d times p entries at all times, and this scales essentially linearly with this product. So that's the, let's say, negative aspects of this filter, but the good ones are, as I said, that it's practical, and very importantly, it turns out that, so people have been using this for quite a while now, you get quite good accuracy, or let's say, you get actually decently good results even with a few number of particles. So again, think of the weather, 10 million degrees of freedom that you want to solve for, and you're using 20 particles, it kind of works. You get a system that kind of makes sense. This hints at something very powerful, because the goal, of course, would be to take more and more particles, because then you converge to the mean field limits and you have some stable dynamics. So this is the nice thing that you would want to do, but because of budget constraints, you cannot always do this. But why does it still work even when you have a few particles? This reveals something quite important about the structure of the system. This term here essentially takes care of correcting the dynamics with respect to the filtering density. So it takes into account the observations and corrects whatever you have done from the prediction that you get from the first part of the equation to incorporate the knowledge from the signal. But everything gets left multiplied by this covariance matrix p hat, which again in our setting, so the covariance is going to be something which has rank p, right? Because you're using 20 particles and the state space is dimension d. So it is at most, let's say, a rank 20 object. So this means that at a deep level, correcting about 20 directions is enough information to be able to stabilize the system and have it track successfully the dynamics. That's a really powerful feature of the systems, and hence that there is indeed this kind of low rank structure in the system. And that is something that you want to exploit, but again, the important part, in the case of the ensemble Kalman, you are not currently exploiting it. Because as we said before, if you want to simulate more particles, the cost scales like d times p. So you don't gain anything. And that is the thing that we want to address in this work. Yes, so essentially, the cost scales like the product, and you don't leverage any low-rank structure. And now we want to do something about this. And to that end, I need to introduce another branch of numerical analysis, which is called dynamical low-rank approximations. The idea is we want to essentially recover this low-rank structure that evolves in time in a quite natural way. And so the construction that we can do is the following. You take any process that evolves in time, you can decompose it here into a mean and essentially this modal decomposition sum. So here the ui's are RD valued functions, the yi's are stochastic processes. And of course, there is a priori an infinite sum of them. But if essentially the coefficients sigma I decay quickly enough, what this means is that you have a very good truncated approximation of your real process, right? You only need essentially R of these terms to approximate the full signal. And here the costs become quite, the cost savings become quite clear if you think again in terms of particle discretization. Rather than having to store a d times p object, what you're storing is here d for the mean. You have R physical modes, as I'll be calling them because they live in RD, so R times D, and you have P particles, you have R stochastic modes which are discretized with P particles, so R times P. This is this model here. You are essentially having a speed up or like a computational saving that is O of R times D plus P rather than the product D times P. And of course, this makes sense if R is small, but we're working under this assumption. You need just a few modal terms to represent your low rank process over time. So this is what we want to do. We want to represent our process in this low rank form at all times. This is actually only a part of the story because you would want to essentially evolve at all times, at all moments in time, your process in this low rank approximation. And so you need to understand what the dynamics are actually on these modes. You need to understand how the physical and the stochastic modes evolve in time in order to never have to essentially recompose the full object. So see essentially this d times b in your equations, because else you've lost. And this is the work of some of my colleagues and my advisor, where they have actually verified that if your process has this low rank structure at all times, and it satisfies this stochastic differential equation in a general setting, then actually you can characterize fully the evolution of the physical and the stochastic modes over time. So you essentially know how these guys evolve without having to assemble and see the full stochastic process. So you're doing exactly this. You evolve a low rank representation of your process at all moments in time. So we wanted to take this idea and extend it to the case of the Kalman filtering, and we're going to be doing exactly this. There was essentially a first step of the process, which consisted in looking at extending this whole idea of deriving these equations for a case of having also some observation stream that appears into it. I'm not going to go into those details because it's a bit technical and not very interesting for our purposes. But then you can apply it to the case of the Kalman VC process that we've seen before, so this auxiliary process, and you get these equations here. So you have, as promised, this low rank approximation of your process at all moments. So here the mean, here the physical modes, here the stochastic modes. One evolution equation for the mean, which looks very similar to the one that we had before, and here essentially an evolution equation for the physical and the stochastic modes, which gives you this promised low rank representation of your process at all moments in time. So this onto itself is nice that you can simply evolve it like this, but the story actually goes even a bit further, because it turns out that this low rank process is actually itself an inhomogeneous Ornstein-Uhlenbeck process, and this means that it's again Gaussian actually. And what this means is that, well, you just need to characterize its field and its covariance, and you've again solved the filtering problem for this low rank process. This is what we then did next. So you have again here the equation for the mean, which is the same as in the first line, so nothing new here. And then you can verify that the equation for the covariance actually has this form. So it's very similar to the one that we had before, the Riccati equation, just that now this last term here is projected left and right onto the range of the covariance. But this is, to me, a rather successful example of a model order reduction, because you started with a process which has some nice properties, so you know it has a mean and covariance equation. You looked at an approximation of this process, and then you derived the corresponding statistics of this low rank approximation, and you get very similar equations or a very similar structure. That is a nice feature. The story actually goes even a bit further, because you can even make more computational savings by realizing that the covariance itself has a low rank structure. So in essence, you can define this low rank gram matrix here, which I call my, and then actually all you need to do is to solve for this time-dependent Riccati equation now. So you have again an equation for the mean, the physical modes, and the now rank-reduced small r times r square Riccati equation. And this essentially characterizes the whole system. This is the first, essentially, theorem, argument, or selling point that I want to bring to you. If you need to solve a large-scale data assimilation setting, you can do so by essentially solving this set of equations, and it gives you a good approximation quickly. I should also mention that we realized, so after deriving these equations, that they have already been proposed in a different context, so for a different situation. We just essentially got to there through a different point, and our derivation allows us to understand essentially why this low rank process makes sense in that setting. So this is also nice. Right. At this point, I'm just going to show you some numerics. So maybe at this point, I should also say that this work is still quite a bit more theoretical, and the examples are a bit more academic than the nice real data sets we've been seeing in the past few presentations. But the idea is still to essentially bring it over to some very concrete applications, either in air pollution or stuff like this. So we're working towards this. Okay, so what we do is we take a PDE, which is just an advection with some reaction term, and we discretize it using some open finite difference. And this essentially gives us some dynamics that you can see here. So you have here the initial condition, time t0, the blue line, and then it gets shifted, and there is some non-trivial essentially smoothing that happens, and that is the signal. And that is the guy that we want to track over time. We assume that we have full observations with some noise, it doesn't matter too much, and that we have some low rank initial condition. That's the setting. And then the first thing that you can check is the fact of, do you have a low rank structure, and can you actually get good approximation results? So to this end, what we do is we take this model, we say that we have a certain fixed model noise here. So I should have said this here, essentially the sigma here is not fixed. We fix it to something, so 10 to the minus 3, and we let the rank vary, and we see, do we actually have a low rank structure that appears? And the answer is pretty convincingly yes. So if you look here on the left, what I'm doing is I'm comparing the mean of the DLR solution of the reduced model and the FOM, the full order model, as they evolve in time. And you can see here, if you use a very small rank, then essentially you're committing a big mistake over time at the beginning. But as soon as you increase the rank, so r equals 7, the error is already much smaller. With r equals 15, you can barely see it. And r equals 25, then essentially you're committing no error. Of course, at this moment, since you're having the exact rank, you're essentially computing the full model, and then you have no real gains. So there is a balance to strike between trying to find this good rank that gives you enough information. What I've said here for the case of the mean also holds true exactly verbatim for the covariance. You can see how, as you increase the rank, your error in the approximation of the covariance decreases. And that is, again, a good feature. So right now what we've been doing is we've been just looking at the difference between the full order model, so the Kalman BC process, and its DLR counterpart. And now we can also assess how well it does at tracking the actual signal, so how good it is at solving the filtering problem. And the main message here is again that it does a rather good job. So you can see here on the left side we're using this RMSE metric. The blue line, which is the one that is going down here, is the brown line is the FOM model. And you can see even with like a small rank, you're already following pretty much close, very accurately, the same level of RMSE. So you're committing pretty much the same level of error as you would with the full order model. So this is again a good news in this domain. And the plot here on the right essentially is looking at another version, another flavor of this RMSE. And the point here is that you do actually observe a speed up, so it is quicker to compute. So the x-axis here is time, and the y-axis is this integrated RMSE. And essentially, because we were not using a very big model, so the dimension d here was 100, then this means that even with like a moderate rank, the speed up cannot be like much more than 10 times, but you do actually see that you are quicker when you use this low rank approximation. And of course, it becomes more and more dramatic a speed up if you take much more high dimensional models. So all of these results essentially go into the way of saying that we pretty much get the type of results that we're expecting. Another thing that I should speak about is we are doing a model order reduction. We are trading our original exact model with a simpler one, or like one which has nice computational properties. You should also be able to predict how bad your approximation is going to be. So I should essentially claim, I mean, how big is the mistake, the bias going to be between your full order model and the reduced one. And without going into the details of that, essentially it boils down to comparing at the end of the day the dynamics of your original full order model and your DLR, the reduced order model. And then essentially you can see that it really boils down to this term here in the middle being different, which is the model noise. So here you have essentially the original one, and here you have PUT, which is the projection onto the range of the physical modes which evolve in time. That's a bit of a tricky quantity to estimate, but the idea is that if this mismatch, so the part that is different between the first line and the second line, is small over time, then actually you can get this class of results where you can predict how much different your mean of the DLR is going to be from the mean of the FOM, and similarly, how different your covariance of the DLR is going to be different from the DLR of the covariance. Sorry, from the covariance of the FOM. And yeah, so essentially this means you don't commit too much of an error if those dynamics match in the beginning. One thing that I should again say is that we are again working in this assumption that we have a small model noise, because this is a somewhat more typical setting, at least for the applications that we've been looking at. So this here will be typically true in practice. We can still verify numerically that this holds true. So now we get back to the experiment from before, but we flip the script and we fix the rank to some value, and we just let essentially this sigma take bigger and bigger values. And essentially, as sigma becomes bigger, what you expect is that the approximation becomes worse and worse because you have a bigger and bigger mismatch. And that is, in fact, exactly what you observe here. You can see here for essentially no model noise, you have essentially, you almost recover very quickly the correct guy. If you have a small one, you also eventually recover it, but if it's sigma equals 0.1, you stay constant, and if it's 0.5, you actually explode. This is again comparing the DLR mean to the DLR FOM, and you have again strictly the same story with the covariance. Essentially, if it's small enough, then you recover the correct guy, but if the model noise is too big, eventually you diverge. So this is again a way of saying that we do get the result that we're expecting. Okay, so this is the first part of the results that I wanted to show you. And now the second part is we wanted to extend this idea of particle-based simulation to the world of the to low rank dynamical low rank systems. And so I won't go into too much of the details, but essentially before we had this low rank process, and now we want to replace it by a low rank particle system. This is the whole idea. Eventually you can work around the math and realize that this amounts to taking this yt that you had, so the stochastic modes, and replace them by a set of p particles. And then essentially, there is some details, so you can essentially define this new low-rank ensemble as the x hat, which is the sample mean, plus the modes, which are still the same, the physical ones, and now the y hat t, which are an ensemble of p particles, are of those. Then essentially, so here there is nothing much to derive, you just have to like work a bit around, and eventually we proposed this set of equations here, which have some really nice property, which is the fact that if you recombine them in the correct way, you can understand what the actual particles are doing in the Avian space. And in essence, this is very similar to the dynamics that we had for the ensemble Kalman, just that again, the difference is that here you have this projection onto the u of t. Then we also verified some other stuff about the well-posedness of the system, and there are some other properties that are nice. The key aspect of this framework is you have the following property, which is the fact that you want to essentially understand how this system behaves as you take bigger and bigger particles. So specifically, what you expect is that you converge to some kind of mean field limits as you take an infinite amount of particles. And those results are typically called propagation of chaos results in the world, in this type of dynamical systems. And they do exist essentially for the ENKF. So this is some nice work by Del Moral and Trigo, where they prove that, in essence, as you increase the number of particles, your system behaves more and more like its mean field limit. So you take two particles to let them evolve according to the ENKF or the mean field. You get this decay that is of order p to the -1/2, exactly what you would expect. And so essentially using very similar tools, we managed to get pretty much the same result for our reduced order model setting. So you have this exact nice property that this DLR ENKF system asymptotically converges to its mean field limit, which is the DLR KBP. And that is again nice. And so this is the theoretical results, and you can in fact also verify it to hold true in the numerics. So here we have taken the same example, taking the DLR ENKF version of it, and you can see how, as you increase the number of particles, you get exactly the same decay, Monte Carlo-like. So this is yet again a nice confirmation. Okay, now I just want to spend the last few minutes to discuss the second example that we have. which is again based on this idea of looking at air pollution models. So this one here is a bit more advanced, as we are looking at the discretization of a 2D finite element discretization. So you have a signal which is given by this advection diffusion model here. We discretize it using a finite element method, also on a higher grid, and there is quite a few sort of bells and whistles that you have to play to make it work. And we're looking at two different observation models. So one is either full observations and the other is partial, because we wanted to essentially look at the effects of so what happens when you're also looking at partial observations, which is the typical setting that you have in most applications. And then there is some extra details we can maybe discuss later. And here are the results that are important to show. So we essentially run three different models. The first is an ENKF with 10 particles, so it has rank 10. And you can see here it's a blue line on the right. So I should say on the left you have the full observations, on the right you have the partial. The conclusions are the same, so I'm going to focus on the right because it's a bit more clear. You essentially, so for the form with p particles, you essentially have a rather big spread in the RMSE. So the metric we're using is the RMSE and comparing its mean and the standard deviation of the RMSE. You can see when you use 10 particles, you essentially have a rather big spread because there is a lot of stochastic fluctuations which come from essentially the little number of particles. And if you increase this number of particles to the form model with 425 particles, then essentially this looks much nicer because you're reducing the spread. You're converging to the mean field limit. That is what you expect to see. And then we kind of wedge a model in between this, which is this DLR ENKF model that we use with a rank 10, but a number of particles equals to 425. And, well, you're not seeing an orange line because it is actually superimposed underneath the green line. So this means that actually, even though you're evolving an object of rank 10, just like essentially the first form model, it has essentially the same properties as the second model, which uses a much bigger number of particles. So this is the really cool aspect. You are indeed managing to leverage the low-rank structure that you see in the system and managing to essentially follow the evolution of those modes at a reduced cost. And as I said, the history is essentially exactly the same if you look at the case of full observations. It's just that the system has a better properties in terms of observations, so the spread is less large, but it's the same story. So this is really encouraging. So just to conclude and recap, we have done essentially this work of looking at so firstly developing a a system of data of DLR that is compatible with data assimilation. We have applied it to the case of the Kalman VC, and then derived its moment equations, leading to a first set of concrete equations to actually solve the filtering problem at a reduced cost. And then we have also proposed an ensemble formulation of the system, which has some very nice properties that can allow you to do some nice analysis, and in particular prove this propagation of Keras results. And currently we're now working on doing some nice extensions and some work with which involves some parameter identification with some a bit more advanced simulations in hemodynamics. And I think this concludes my talk.
All right, we have time for very few questions. It was fast. It was a lot of material to absorb.
Yes.
I think we need a bit of time to think about this. Yes.
Giving a try. You are saying that you are looking to apply it now to hemodynamics.
Yes.
Right? Are you considering thrombs, like, thrombosis?
No. It's more going to be a model of essentially all of the major arteries of the system, and you want to do some inference on essentially the frequency of the.
Maybe a general question about the drawbacks
of
this low-rank approach. So, what are they, and how do you see them?
The drawbacks. So, one thing that is not always easy is firstly to know what the correct rank is. So that is always a big question. And if you're essentially, fixing a rank and then it's the wrong one, then you might go into some very wrong direction, which does not reflect the truth anymore. So there is, of course, some non-trivial work which goes into understanding how do you choose the correct rank.
And how do you do it in practice?
That is a very good question. that is not so what we focus on, but I mean there is some work which looks at dynamic ways of increasing or reducing the rank to seeing what is the correct, what is the good rank in a sense.
And may I ask, how do you score the predictions?
How do you mean this?
So you have a probabilistic prediction,
yeah,
and well, you have an observation.
Mm-hmm.
So then, how do you evaluate that your probabilistic prediction is doing the job?
I mean, this is just given by the model and the dynamics. This is not something that you. I mean, there is no decision to be made at this moment. You just incorporate the data.
In terms of evaluating the predictions, when you see the data,
Mm-hmm.
you see the actual responses. Your probabilistic model is giving you a distribution.
No, so there is no response. I mean, you're just essentially like observing the filter of data, I mean, the stream of data, and you want to use it to update your knowledge of the model. I mean,
but you have information coming in at some stage.
yes. I mean, okay. I'm still not quite sure I understand
Well,
that.
we'll take
Yeah,
your time.
absolutely.
Thank you so much.
Thank you.